So this is to chair the session on pairings. I'm Francesco Sica, and today we have 3 talks. So the first one is by Ratash Datta and Tapas Pal on decentralized multi-authority attribute-based inner product FE, large universe and unbounded. So Tapas is going to give a talk.
Yeah,
thank you very
thanks
much.
for the introduction. Okay, so I am Tapas from Entity Japan. So I will be presenting our paper, Decentralized Multi-Authority Attribute-Based Inner Product FE, Large Universe and Unbounded. So it's a joint work with Pratish from Entity Research. So let's start with the syntax of function encryption, which is an advanced form of usual public key encryption. So it has 4 algorithms. So in setup, authority takes security parameter lambda as input and computes a master public key MPK and a master secret key MSK. So using MSK, the authority generates a secret key escape corresponding to any function f and sends it to the user in the system. Using MPK, we can encrypt message M and publish our ciphertext CTM. Now, a user holding SKF can decrypt CTM and learns functional value of the message M. Okay, so informally, security of FE guarantees that a user holding SKF cannot infer anything else about the message M from the ciphertext CTM except the functional value of the message M. So inner product function encryption or IPFE is a particular class of function encryption where secret key and ciphertext are generated corresponding to some vectors Y and X there. And during decryption, a user recovers inner product between the vectors. So due to this functionality, SKY reveals the inner product value, right? So therefore, if we release sufficient number of SKYI, then we can solve this system of equation for X using simple Gaussian elimination, and hence the system is completely broken, right? So in other words, that the leakage in IPFE is very high. That means we cannot release SKY for n linearly independent Y vectors. So to control this leakage, Abdal et al. In Issue 2020 proposed this notion of attribute-based IPFE, which provides attribute-based access control on top of IPFE. So here secret keys and ciphertext are additionally associated with attributes, ATT and policy P respectively. And during decryption, we recover the inner product value given that the attribute of the secret key satisfies the policy of the ciphertext. So in the security model, the IPFE game condition inner product of X0YI equal to inner product of X1YI is required to hold only for the secret keys where the associated attributes satisfy the policy of the challenge ciphertext. Okay, so it means that we can control the leakage to some extent, meaning that we can release SKY for n linearly independent Y vectors unless all the associated attributes satisfy the policy of the challenge ciphertext. Okay, so let's consider an application of ABE IPFE in the domain of IOMT or Internet of Medical Things. So let's say there is a company who wants to increase the efficiency of a wearable health device, and for that it hires a set of hospitals, H1, H2, research labs, L1, L2, and the user's data, I mean the patient's data, for example, blood pressures are encrypted by the device under a certain policy P, and the ciphertext is uploaded to the server. Now, keys are provided to the users of the system, who are the doctors of hospitals and researchers of the labs, corresponding to their attributes. And the user will be able to decrypt the ciphertext. That means it can run some computation over the encrypted message, given the attributes satisfy the policy we are considering here. But the problem in usual ABE IPFE is that all the attributes are controlled by a single authority. But in reality, different attributes are controlled by different authorities, right? So, for example, hospitals controls attributes related to their departments, labs controls attributes related to the seniority level of the employees. And another drawback of normal ABE IPFE is that if at any point of time the authority is corrupted, then no security of users' data can be guaranteed. Okay, so to mitigate this problem, Agarwal, Goyal, and Tomida in TCC 21 introduced this notion of multi-authority ABE-IPFE, where we have multiple authorities in the system. Each authority is responsible to generate secret keys corresponding to the attributes under their control, and the secret keys are associated with a global identity GID. So during encryption, encryption is performed using a set of public keys of the authorities who control some attributes related to the policy under consideration. And during decryption, a user combines a set of secret keys computed under the same GID and same Y, and it can decrypt the ciphertext only if the associated attributes satisfy the policy of the ciphertext. So in the security experiment, instead of interacting with one single authority, the adversary can ask secret keys from many authorities, given the the IPFE game condition only required to satisfy if the set of attributes satisfy the challenge policy. And additionally here, the adversary can corrupt some of the authorities, given that the attributes queried by the adversary from the honest authorities, along with the attributes controlled by some corrupted authorities, does not satisfy the policy of the ciphertext. Okay, so now if we replace ABE-IPFE with ABE-IPFE in the application of IOMT, it means that the hospitals and labs are now treated as individual and independent authorities who controls the attributes which they are managing. So, for example, ATT1 is controlled by hospital 1 and ATT2 is controlled by lab 2. Now if hospital 2 and lab 1 are corrupted, the system remains still secure, right? Okay, but the only existing construction of ABE-IPFE by Agarwal et al. Has some limitations. Firstly, the length of the vector, which is n, is bounded, is fixed at the time of setup. So as a result, the master public key size of each authority depends on this bound n, and the ciphertext size goes with respect to this n, even if you have a vector whose size is much less than n. Secondly, each authority controls only a bounded number of attributes in their system. So they support only small universe of attributes. And lastly, they build the primitive in the composite order pairing groups, which slow down the performance. More specifically, the encryption time took 2 hours, and decryption time is huge, which is 5 days. Given we take a vector of length 200 with a reasonable security level. Okay, so in our work, we overcome these limitations. In particular, we construct ABE-IPFE, where unbounded length message and key vectors can be processed, meaning that the public key size of each authority is constant and the ciphertext size is input specific. Authorities are allowed to control arbitrary number of attributes, and attributes need not be enumerated at the time of setup. That means we support large universe of attributes. We construct this primitive in prime order pairing groups, and we prove security under target group based assumption. In particular, we prove static security under the decisional bilinear development type assumption. So here static security means that adversary is restricted to query, restricted to submit all its queries at the time of system setup. The only existing construction of ABE-IPFE by Agarwal et al. Satisfies selective security, where all the queries of adversary is static except it can query keys selectively. Okay, so this is the roadmap of our paper. We first construct a small universe ABE-UIPFE. Here U stands for the unbounded length vectors. We construct this primitive under the standard DBDS assumption, and we prove static security in the random oracle model. Then we upgrade the small universe scheme into a large universe scheme under the parameterized version of DBDH assumption, which we call LDBDH in our paper, and we also show generic security of this assumption in our paper. So for the interest of time, I will only focus on the small universe scheme in this talk, and for large universe scheme, please look into our paper. Okay, so as an initial attempt, we try to combine the MAB of Dotto Komorowski Waters with the unbounded IPFE of the person and points world. So the idea is that first we fix a parameter S, which is the maximum number of gates in the policy. Policies are represented as linear secret sharing access structures, and it has two components. One is the matrix M of order L cross S, and rho is the row leveling function. Okay, so during setup, authority samples a few scalars, AT, UTJ, runs from 2 to S. These are the master secret key for the authority, and the corresponding group exponentiations are the public key. So during secret key generation, with respect to a GID, Y, and attribute T, we use a hash and exponentiation procedure to vectorize the scalars of master secret keys. That means we vectorize AT using hash function H1, and we vectorize UTJ using hash function H. Here, hash function H1 takes T, which is the attribute, as input, and H takes the GID and Y as input, where K is the common input, which is the indices of the vector Y. So during encryption, the encryptor samples some randomness Ri, and it also samples two matrices V and X, where the columns of V are the secret shares of the vector Z, and the columns of X are the secret share of zero vector. So we first mask the message vector X using Z, and then we encode the matrices V and X in C1i and C3ij using a hash and pairing technique with the help of hash function H1 and H. Okay, so now if we have a set of secret keys where the attributes satisfy the policy of the ciphertext, then we can reconstruct the coefficient Wi. And using this coefficient, we can now compute the masking term, which is the inner product between Y and Z using this pairing product equation. Okay, so now you see that there is a problem in this construction because we do not know GID and Y at the time of encryption, right? So in particular, we cannot use hash and pairing mechanism to vectorize the component UTJ. So for that, we devise a hash decomposition mechanism where we write the hash function H as a product of two independent hash functions, H2 and H3, where the inputs of H2 are known to the encryptor and inputs of H3 are known to the authority. So using these two hash functions, we will now we can vectorize UTJ into two vectors, UTJ2 using hash function H2 and UTJ3 using hash function H3. So since these two hash functions can be computed by the authority because authority knows all the inputs, then we can replace the secret key component by the element-wise product of these two vectors. But we cannot simply replace the hash function H by H2 during encryption, right? Because in that case, decryption will not work. So for that, we look into the decryption equation, in particular the term involving C3ij, and we recompute this pairing with the help of hash function H2 replacing the hash function H. Now in this equation, you see that Y is not known to the encryptor, right? So if we remove Y from this equation, then C3ijk can be efficiently computed by the encryptor because encryptor knows all the inputs of the hash function H2. Okay, now last thing is to handle the hash function H3, but not all the inputs are known to the encryptor. So for that, we sample another layer of secret sharing of 0 in the form of a vector, and we encode this vector in C4ij using UTJ. So these elements plays an important role in the cancellation of UTJK3 of secret key during encryption. Okay, so due to this introduction of new hash functions H2 and H3, the decryption equation will now change. It will involve both hash function H2 and H3. So H2 is implicit in C3ijk, and during decryption we will compute. Okay, so this is the final scheme of our small universe MABE IPFE. So here we note that the size of public key for each authority is constant. Secret key is succinct, it contains only one G2 element, and the ciphertext size is input specific. Yeah, so I will conclude my talk in this slide. So we define and construct a large universe MABU IPFE with constant size public keys, succinct keys, secret keys, and input specific ciphertext size. We allow each authority to control arbitrary number of attributes, and we build this primitive in prime order pairing groups. And we prove static security under a DBDH type assumption, which is a target group assumption. And target group assumptions are known to be qualitatively weaker than source group assumptions considered by previous work of Agarwal et al. Okay, so I will finish my talk with a couple of open problems. So we achieve static security in our paper. So it is an interesting direction to consider selective or adaptive security under target group based assumption for the primitive. Another interesting open problem is to see whether we can achieve adaptive corruption from standard assumptions. And of course, it is a really challenging problem to consider. That means whether we can construct MAAB IPFE or MAAB UIPFE from post-quantum assumptions such as lattices. Yeah, with that, I will finish my talk. So thank you. If you have any questions, please ask.
And from the audience? No. So, okay, let's thank the speaker again.
Thank you. Thank you.
Okay, so our next speaker is Nikhil Vanjani, who with LNG is presenting work on multi-client inner product encryption, function hiding, instantiation without random oracle. So thank you, Nikhil. The floor is yours.
Yeah. Thank you. I'm Nikhil Vanjani. I'm a second-year PhD student at Carnegie Mellon University, and I'm going to present my work on multi-client inner product encryption, function hiding instantiations without random oracles. This is joint work with my advisor, Elaine Shi. Let me introduce the problem of multi-client functional encryption with a motivating example. So suppose that there is a medical research organization that has partnered up with N hospitals, and it wants to compute some functionality on the patient data that it collects from the hospitals. And suppose that this data is streaming, meaning that there are some time steps T associated with every data that the hospital sent. And the functionality is also based on these time steps. For example, the data could be about daily number of cases reported by every hospital, and the organization could want to learn some linear regression model to predict the number of cases in subsequent days. So if we do not care about the privacy of patient data, what we can do is all the hospitals can just send the data in the plane, and the organization can compute the function as it is. But we know that patient data is often sensitive, and we can't give it out to the organization in plain. So what can we do about it? Well, a simple idea could be that we can have all the hospitals encrypt the data and send to the organization. But then the challenge is, how can the organization compute on this encrypted data? We know that traditional encryption provides you all or nothing access to encrypted data, meaning that if you have the decryption key, then you can learn everything about the underlying plain text, or if you do not have the key, you learn nothing. Whereas over here, we need to provide some fine-grained access control to the data, meaning that the organization should be able to learn only a function on the messages, not all the messages themselves. And As introduced in the previous talk, functional encryption provides a way to solve this problem essentially. What we have over here is we can use a master key to come up with some functional keys for function f. And then these functional keys can be used to decrypt a message x to learn only f of x and know more about the message. And if we want to consider the case of multiple clients, then multi-client functional encryption provides a way to generalize to this setting. What this means is instead of a single ciphertext, now we have n number of ciphertexts that we want to decrypt. And the functionalities that we will learn is f of x1 through xn instead of just f of x. So over here, we have some time step t associated with all of these messages. The reason over here is that we want to control what the decryptor can learn. So if the decryption is performed on n ciphertext corresponding to the same time step, then you can actually learn the functionality. If you try to mix and match ciphertext from different time steps, then you should not learn the function output and you should just get some garbage value. This will ensure that the ciphertexts are used as intended. So let me introduce the 4 algorithms involved in MCFE with the motivating example I showed. So there's a setup algorithm which is run by a trusted authority. It outputs a master key to the trusted authority and n encryption keys, 1 to each client, in this case 1 to each hospital. Now suppose that all the hospitals have their encryption keys and they want to encrypt a bunch of messages x1 through xn for some time step t. What they can do is they can perform a locally encryption algorithm with their keys to come up with these ciphertexts highlighted in this gray boxes and send the ciphertext to the research organization. Now that the research organization has all the ciphertexts and say it wants to compute this function f on it, it can send this request to the trusted authority, and the trusted authority can use its master key to run a keygen algorithm and come up with a functional key, which it can send back to the research organization. And now that this organization has the key and all of the ciphertexts, it can run a local decryption algorithm to learn the function f of x1 through xn as required. So this is how we can use multi-client functional encryption to solve this problem. Now, those who are familiar with fully homomorphic encryption could ask, how is this different from that? The difference is that over here in MCFE, when you run some computations on encrypted data, you get f of x1 through xn in the plane, whereas in FHE, you get encryption of f of x1 through xn. So that's the key difference, and that leads to differences in what are the application scenarios for both. So I hope by this point of time, I have motivated to you that MCFE is an interesting cryptographic primitive to study. Now, in our paper, we study the function hiding security of MCFE. Intuitively, what this means is the ciphertext for x1 should hide the message x1 and so on for all the n messages. Further, and more importantly, the function key for f should hide the function f. And the decryptor should learn only f of x1 through xn and know more about the messages x1 through xn and the function f. Secondly, we study function hiding security of MCFE for a specific class of functions called inner product functions, as introduced in the previous talk. So inner products are as follows. We have a vector y, which is comprising of y1 through yn, and the functionality then is just inner product x1 through xn with y1 through yn, and this is just the sum of xi yi for all I and n. Now you may ask, why is function hiding MCIP interesting? Well, it's interesting when we want to perform when we want to delegate computations to an untrusted server, and more specifically, when the decryption inherently needs to be performed by some untrusted server, this function hiding security is interesting. Let me give you a quick example. So Xi and Wu considered this notion of non-interactive anonymous routing, and they proposed a new model to capture anonymous routing as follows. We have n senders and n receivers who are trying to communicate anonymously with each other. And this task needs to be facilitated by a single untrusted router instead of a bunch of routers. And they showed how to use multi-client functional encryption, which is function hiding, for a specific class of functions that is selection function. And they showed how it can be used. The idea over there is each of the senders can send the destinations that they want to talk to this trusted authority. And based on that, it can come up with this permutation pi and a function key for this permutation pi, which it can send to this untrusted router. Now, clearly, this function key that is providing to the untrusted router should not reveal the function that is the permutation over here for obvious reasons because of anonymity. And hence, in such scenarios, function hiding MCFE is interesting. So what do we know about function hiding MCIP? We have only one construction so far by Agrawal, Goel, and Tomida. They showed how to construct it from standard assumptions on bilinear maps. And to prove security of their construction, they had to make two significant relaxations. The first is they could only show how to prove it to be selectively secure. We won't go into the specific details of selective security today, but all you need to know is selective security is imposing some strong restriction on the adversary's capabilities. Secondly, they showed how to prove it in the random oracle model. And we use random oracles as a heuristic, but we know that random oracles do not really exist. So the question then is, can we construct a fully secure function hiding MCIP from any standard assumption in the plane model? And we show the first such result. We prove fully secure function hiding MCIP from standard assumptions on bilinear maps in the plane model. So the roadmap for rest of the talk is going to be as follows. To build some intuition, I will first show some warm-up exercise, and then I will show how our construction works. And lastly, I will briefly talk about how to prove security of our construction. Let's start up with the warm-up. First, I will tell you about a naive scheme that is going to be insecure, and then I will briefly talk about how the previous work makes that scheme secure. So for the naive scheme, what we will start with is just function hiding inner product encryption. This is a special case of MCFE where there is only a single client. Specifically, now what we have is just a setup algorithm outputs a master key, which also acts as the encryption key. The encryption algorithm is same as before, and we get a ciphertext. The only difference is that now the encryption algorithm does not have any time steps T associated with it because there is only a single client. Second, the keygen algorithm is also same as before. The only difference is it operates on a unary function, y1, and outputs a key for y1. And the decryption algorithm outputs inner product x1, y1 instead of sum of a bunch of inner products. So the warm-up that we will do is, can we simply use n instances of inner product encryption, one instance for each client, and what can we get out of this? So what we can do is, in the trusted, in the setup algorithm run by the trusted authority, it can run one setup of IP for each of the instances and provide one master key to each of the clients. And the master key of the trusted authority is just the union of all of these keys. Equipped with these keys, the hospitals can locally compute the encryptions on their messages. Then suppose you want to compute a functional key for y equal to y1 through yn. What you can do is observe that each yi corresponds to the ith client. So we can use the ith client's master key of the IP to come up with a function key. And then the function key for y will be just the union of all of these keys. And now that the organization has all of these ciphertexts and the keys, what it can do is run the decryption of all of these instances locally and obtain inner product x1, y1, and so on up to xn, yn, and just sum up all of these values to obtain the desired output. Well, the hope then is that if the underlying IP is function hiding secure, then so should the resulting MCIP scheme be. And it turns out that this scheme actually suffers from three problems. First, that it reveals every user's inner product, as we just saw in the decryption algorithm. This is leaking more info than intended by the functionality. Second, it allows mix and match of ciphertext across different time steps. This is because we did not use time steps in any way so far. Thirdly, it allows for mix and match of function secret keys. This is because the function key was just a set of keys, and there is no way to prevent mixing across two different sets. And the previous work resolves all of these three problems by coming up with some coordinated randomness among all the clients. Crucially, it comes up with this coordinated randomness using hash functions that need to be modeled as random oracle for their paper. So the question then is there an alternate way to coordinate randomness, and how to prove security for such a scheme? And let me show how we can construct our scheme. So to coordinate randomness, we will use a new building block called correlated PRFs, and we will show how it can be used. So correlated PRFs is similar to just normal PRFs. It has two algorithms, setup and evaluate. The setup algorithm outputs a bunch of PRF keys, and the evaluation algorithm can evaluate on some messages T. The interesting property compared to normal pseudorandom functions is that the sum of evaluations now on the same input is going to be 0. Secondly, if you use different inputs T and try to sum up all these Ki of T values, then the sum is going to be junk. And it was shown in some previous papers that CPRFs can be constructed from standard PRFs. So how can we use CPRFs in our scheme? The idea is to expand the vectors by one more slot. And now the client 1 will encrypt not x1, but x1, k1 of T. And over here, T is the time step T. And so on for all the n clients. Next, for the function keys, for the first client, it will be corresponding to y1, z, and so on for the nth client, it will be for yn, z. Crucially, note over here that z is shared by all of the clients, which is okay because the function key generation is performed by a trusted authority. Secondly, this is fresh and random for each of the queries. What this results in is the partial decryptions have these red masking terms that we see. And when we sum up all of the values, the masking terms cancel out because of the property of correlated PRFs. Now, is this scheme secure? It turns out that to prove security, we need to argue that each of these masking terms look random for all honest clients. And as I mentioned earlier, we are using all of these black boxes are inner product encryption schemes, which are function hiding secure. And all the function hiding IP schemes we know are from bilinear maps. And when we instantiate with any of these schemes, we run into a problem that these terms do not look random due to some DDH style attack. So the solution then is we want to encrypt each of these KIT. And what we have now is the client 1 will encrypt x1, k1t plus a1r1, r1, and so on for all the n clients. Here, these AI values are part of the client encryption keys, and RIs are just some randomness. Now, how does it look to be an encryption of KIT? Note over here that the IP scheme we use is for computing inner products in the exponent, meaning that what we are actually computing is encrypting this vector g raised to x1, g raised to k1t plus a1r1, g raised to r1. And now these second and third terms look like El-Gamal style encryption. So this intuitively captures how we are encrypting these KI values. And correspondingly, for the function keys, now we have y1, z, minus z times a1, and so on for the all n keys. What this ensures is the correctness is preserved as follows. Now, when we perform partial decryption for the first client, we get the first two terms as before. We additionally get two other terms which cancel out among themselves because all of those values are scalars. And hence, the correctness still holds. So this is our construction. Now, let me quickly tell you about proving security. It turns out that proving security is non-trivial, and we first prove selective security of our scheme and then show how to prove full security. While I won't go into the details of the security game today, I can just mention that full security considers any sequence of keygen and encryption queries by the adversary, whereas selective security requires all keygen queries to be sent before any encryption query. And the key insight then is, because you are sending all keygen queries ahead, you can embed the inner product x1 y1 in the first client's ciphertext and then try to come up with a sequence of hybrids to prove security. This new sequence of hybrids that we have requires a key identically distributed step. And to enable this step, we use the randomness of K1T and Z to come up with some masking terms to perform this step. Secondly, for full security, because keygen queries can't be sent ahead of encryption queries, we can't embed the inner product x1 y1 in client 1's ciphertext anymore. So we need to come up with a new sequence of hybrids. For this new sequence of hybrids, we also have some identically distributed step, but it turns out that these masking terms, we can't use them as before. So the key insight then is we open up the black box of function hiding IP and use the randomness of the function keys in this IP to enable the identically distributed step for this new hybrid sequence. This completes the technical part of the talk. Let me quickly tell you about some other results in our paper. So you can find the formal security definitions and proofs in the paper. Lastly, the scheme I presented to you today was under a certain restricted scenario. It requires the adversary to abide to some all or nothing admissibility rule. And in the paper, we show how to remove this rule using all or nothing encryption. This also requires constructing a new AONE scheme, and we show how it can be constructed. Lastly, I presented to you today a function hiding secure MCIP from function hiding IP and correlated PRFs in the plain model. This scheme enjoys two really nice properties. It's much simpler than all the previous schemes, and this includes function revealing schemes that have been there before. Secondly, the ciphertexts over here are succinct, and this leads to the first function hiding MCIP from non-lattice standard assumptions in the plain model with succinct ciphertext size. This was not known before. And I will leave you with two open questions. How to handle adaptive corruptions without performing complexity leveraging is a challenging problem. And secondly, how to decentralize the trusted and get rid of trusted authority to come up with dynamic decentralized functional encryption is also an open problem. And with that, I will thank you for your time.
Okay, I think we don't have really time for questions, so we'll move on to the next speaker. Thank you, Nikhil, again. So the next talk will be on GLUE, generalizing unbounded attribute-based encryption for flexible efficiency trade-offs by Marloes Venema and Greg Alpar, and Marloes will give the talk. Thank you very much.
Yes, thank you for introducing me. Can everyone hear me correctly or right? Yes. So I'm Marloes. I will be giving our talk about GLUE, generalizing unbounded attribute-based encryption for flexible efficiency trade-off. I always start my talks a bit with a motivation, which is a sort of very high level summary of the work that I did and also the work that, so why we did this work. So if you cannot follow everything, that's fine. I will explain everything in the talk, but it gives you a bit of an idea of what to expect from the talk. So attribute-based encryption, or ABE for short, is a very versatile primitive. It can actually enforce access control on a cryptographic level, And for that reason, it's actually been considered pretty extensively to securely manage access to data. And what we see in literature is actually various properties that can be supported in ABE. So you can think of, for instance, the unlimited use of attributes, or the support of negations or not. And whether we actually need these properties really depends on the application in which we want to apply it. Similarly, the efficiency requirements also really depend on the application in which we want to apply ABE. And in particular, it might depend on the computational devices. So for instance, if we have really slow decryption devices, then we want to optimize the decryption efficiency of the scheme. Now, typically what we see is that schemes provide a fixed efficiency trade-off, which would mean not so bad if we had like a lot of options in terms of schemes, but in particular, these schemes typically also have a very inefficient decryption algorithm, especially if we want to have many desirable properties. Now, the goal of our work is to create a scheme that can support many such properties, such as negations, with a flexible efficiency trade-off. So ultimately, we can fine-tune the scheme so that it has a very efficient decryption algorithm. So we'll first give an introduction about ABE, so you have some idea on what this is if you don't know it yet. We just had 2 talks that were sort of closely related, so I hope you have a bit enough an intuition on it. Then I will introduce glue, and then I will conclude this talk. So in ciphertext-policy ABE, or CP-ABE for short, we consider a setting with the 2 famous users, Alice and Bob, who want to exchange messages. And we also have that in the ABE setting. But in the ABE setting, we also have something like an untrusted platform, such as the cloud, in which we want to store data. And we also have an entity called the Key Generation Authority, or KGA for short, who generates the master key pair. And this master key pair consists of a master public and a master secret key. And he can use this master secret key to generate secret keys for the users. So in this case, Bob can request secret keys for his attributes, doctor and Johns Hopkins Hospital, and he can store them on his computer. So he can use them later to decrypt things. Now, if someone wants to encrypt something, then she can download the master public key from the Key Generation Authority. And then she can think about, okay, who does she want to share her data with? So in this case, she might have generated some data that she wants to share with doctors and nurses. Then she can specify this in a policy and encrypt the data and put the ciphertext, well, for instance, in the cloud. And in this case, everyone can access the ciphertext, but only people who satisfy the policy and have the keys that sort of show that can decrypt the ciphertext. So in this case, Bob can decrypt the ciphertext because he has a key for the attribute doctor. Now, if you look at this setting, then you already kind of feel like, okay, this is a way to cryptographically implement access control. And that's actually also the reason why it's really popular in settings in which data has to be stored on untrusted platforms. I would like to highlight 2 things. So the European Telecommunication Standards Institute, or ETSI for short, has a couple of years ago published a technical report in which they consider several use cases in which we can apply ABE to enforce access control. And some use cases that you can think of are the cloud, but also IoT. And there are some other use cases in that report. I will also want to point out a recent advancement. So Cloudflare is presented at last Real World Crypto, the new version of the GeoKey manager. It's called Porcinus. And in this system, they also implement access control using ABE. So this is actually something that nowadays is even used in practice and even on a very large scale. Now, if we look at all of these use cases, then we can actually see that many of these use cases sort of have these common requirements that we need from ABE. And one of them is expressive policies. So what we want is that these policies that we enforce on the ciphertext should at least support at least Boolean formulas consisting of ANDs and ORs. We also want to support large universes. So you can basically use any arbitrary string as an attribute. So you can think of names, roles within a company, departments within a hospital, MAC addresses. And we also want the scheme to be unbounded so that there are no bounds on any of the parameters. And typical parameters that might have bounds on them in ABE would be the length of the policies or of the attribute sets. There are also some use cases that require non-monotonicity, meaning that the scheme can support negations or not operators. And actually, something interesting that Etsy says is that we cannot enforce access control with ABE like to the fullest extent because we cannot support negations efficiently. Cloudflare last RWC said, negation is important, please include it. So this is like one of the reasons why we really wanted to build this. Lastly, I would like to point out the storage and computational efficiency requirements, which do not actually have a really common thread in all of these use cases. In fact, we see that they're a little bit different for every use case. So to give some example, in the Portuguese and cloud settings, we really require a fast decryption algorithm, and we may not care much about the efficiency of the key generation or the encryption. But in the Internet of Things, for instance, we want encryption to be really fast and the ciphertext to be small. In this talk, I will mostly focus on this goal of getting a very fast decryption algorithm in your schemes. So that's something. So we want fast decryption. What's the state of the art? So currently, if we do not require negations, then we're pretty much like there. Like we have really good schemes with really efficient decryption algorithm. But if we do require negations, then it's a little bit more complicated. So either we have a very expensive decryption algorithm, and with expensive decryption algorithm, I mean that we require many pairing operations during decryption, or well, some schemes that do support negations are more efficient. They're also more restricted. And then we're back to this bounded thing, like we want schemes to be unbounded so you can flexibly use them in practice. So that's like definitely a drawback there. And to sort of understand why non-monotone schemes are much less efficient than monotone schemes, we can observe them, and we see that these schemes actually have a similar underlying structure. So all of these schemes use polynomials in order to support large universes, and to support negations, you can exploit this polynomial to do that. Well, why are these schemes so inefficient? Well, actually, there's a very strong relationship between these polynomials' degrees and the decryption efficiency. And what we typically see is that higher degrees of the polynomial also lead to faster decryption and vice versa. So to give an example, if you look at the Rousselac-Water scheme, then they're employing a 1-degree polynomial, and they require 2 pairings per attribute during decryption. And the Waters 11 scheme, the large universe scheme in the appendix of the full version, employs an n-degree polynomial, and it requires 2 pairings per n attributes. And note that this scheme is bounded, so you can have at most n attributes in your keys and ciphertext combined. So it's 2 pairings per decryption instance, basically. Now, the reason why unbounded schemes that support large universes and can support negations are like less efficient is that all of these schemes employ a 1-degree polynomial and thus require at least 2 pairings per attribute during decryption. So the high-level idea is, okay, what if we generalize the hash? We replace it, instead of doing a 1-degree polynomial, we do an n-degree polynomial. And that's actually the idea behind glue. So in glue, we replace the polynomial-based hash of the Rousselac-Water 13 scheme by replacing the 1-degree polynomial with an n-degree polynomial. And actually, the scheme that you get by just doing that is not secure. So we also convey another parameter in the Rousselac-Water scheme as a polynomial so that we can actually do proof security. But also note that Rousselac-Water is a monotone scheme. So actually, the reason why we're focusing on this scheme is because it's basically the basis of all unbounded schemes that support negations. And I get later to the point where we actually construct a scheme that supports negations. Now, why does like replacing this 1-degree polynomial with an n-degree polynomial actually lead to a more efficient decryption? Well, like this n-degree polynomial is constructed where n is nk plus nc minus 1. And the idea is that you partition the sets and policies in smaller subsets of maximum size nk and nc, and you sort of like share the randomness of the polynomial amongst every partition. And in that way, we can sort of reduce the number of pairings that we require during decryption by a factor in nk and nc. So if nk and nc are equal, it's actually a factor nk smaller compared to Roussel-Lagasse Waters 13. So basically, the higher the nk and the nc are, the more efficient decryption is. But this is not without a cost, because actually the encryption efficiency will decrease when you make nk and nc higher. But before I get to performance estimates, I will first discuss a bit about the security of glue. So in the security proof, we combine and generalize proof techniques of various works. So most notably the schemes by Waters that I just mentioned, the Waters 11 scheme, the Roussel-Lagasse Waters scheme, and also another scheme that sort of seems unrelated. It's the AC16 scheme. It's a scheme with short ciphertext, but we use the tricks that they do to sort of make the proof work, and we use a new trick to sort of make sure that we can combine all of these proof techniques in a nice way. We also prove security in the symbolic pair encodings framework by Agrabel and Chase, introduced in Eurocrypt 2017. And by doing that, we actually achieve properties like non-monotonicity for free. So we have in this framework, if you have a secure scheme, then you can apply certain transformations and they preserve the security of the scheme. So it's actually pretty cool, I think. Well, now to the benchmark. So we have made some performance estimates for various configurations of glue. So here you can see, like, the lower you get, the higher the nk and nc become. And as you can see on the left side, the storage costs are not impacted, so they're actually decreasing. The key generation costs are also decreasing. And for decryption, we see that the decryption costs are much faster than Roussel-Lagasse Waters 13. So it's like a factor 5 faster here. So if we really want a fast decryption algorithm, we can increase nk and nc. Of course, this comes at a cost. So if you see here, the encryption costs actually do increase, but much less fast than the decryption costs decrease. But still, this is not a number that you might find interesting for your application. So there are some tricks to actually optimize this. And for that, I would invite you to read the paper or come talk to me about it. Also, this is for the monotone schemes. For the non-monotone schemes, we have similar things, but actually for negations, we see an even better speed up in the decryption. Now, to wrap up, so ABE implements access control on a cryptographic level, and it actually can support various different properties that you can sort of choose for various different use cases. So previously, if we wanted to support negations, we couldn't really do that without really impacting the decryption efficiency. And basically, glue addresses the need for support for negations while also having an efficient decryption algorithm. And with that, I would like to end my talk. So thank you for your attention. I'm happy to take questions now.
Any questions from the audience? I have a quick one, maybe the polynomials you were saying that you were increasing the degree. Are there in one variable or several variables, or do you have can you play with a number of variables?
So as in the variables of the polynomial, yeah, so we only have one variable now. I've actually thought about including more variables, but so right now you use one variable for the attribute that you embed in the policy. But if you want, for instance, so there are some schemes that sort of separate the attribute label from the attribute value. And then you can actually, like, maybe it will be interesting to have two variables or maybe more variables. So I've actually also looked into that as a follow-up. Yeah.
Okay. Any other question? No, then let's thank the speaker again. So that concludes the session.
Hi, everyone. So next event on our calendar is the group photo on the Coda rooftop. To not overwhelm the building, we're going to go through in separate groups, slightly delayed from each other. If you're sitting on that side, I'll call you the Sasha group. If you're sitting in the middle, I'll call you the Vlad group. And if you're sitting over there, I'll call you my group. And Sasha's group, I guess, will go first.